Welcome students, welcome to the final lecture on relations. So, finally, we are going to today we will have to see some more things on functions. In the previous lecture, we saw some few facts about what are known as the certain facts like the properties of how properties of functions, how do they behave on intersections and unions. Today, let us take up how the function behaves on the complement. Now, suppose f from you have a function from a set x to a set y. So, if a subset of x, if you have a subset of x, now the question is, does the following hold true? Let us look at a simple. So, the most thing is what we wanted is this one, f of x minus a, is it same as f x minus f a. Does the following equality hold true? Now, before we try to understand this, let us try to look at an example. You consider a map f or a function f from minus 4, the interval minus 4 to 4 to r, given by f x equal to x square. Let us look at this function. Now, choose a as open 0 closed 4. Now, here if you notice x minus a, the complement of a in x, it is going to be close to minus 4 to close to 0, and if you look at f x, it is exactly this much, close to 0 to close to 16, while f of a is open 0 to close to 16. You have the whole thing. Now, if you look at f x minus f a, it is exactly just singleton 0. On the other hand, if one tries to compute f of x minus a, it is going to be close to 0 to up to close to 16. What we have noticed here is that f x minus f a is properly contained in f of x minus a. This is what we have observed through this example. Now, the following question is it always true for all function f? So, is f x minus f a contained in f of x minus a for any function f from x to y? In fact, the answer is yes. So, let us try to prove this. Let y belong to f x minus f a. That implies y belongs to f x, but y does not belong to f of a. Now, what we have is y in f of x, the image of x under f, that immediately implies there exists at least one x in an element of capital X, such that y is of the form f x. Now, on the other hand, y does not belong to f of a, that immediately implies there does not exist any in an element a in a such that y is of the form f of a. Therefore, what these two statements implies that x belongs to x, but x does not belong to capital A. What we have? We have produced an element of capital X which is not in A, whose image is y. F x belongs to f of x minus a. Thus, f x minus f a is contained in f of x minus a. Fine. Now, let us look at the two things what we had. F of a intersection b is contained in f of a intersection f of b, and the second one f x minus f a is contained in f of x minus a. What is that is lacking for a function so that equality hold in these cases, right? Or what is that we need more on f so that equality actually holds? Let us look at the example that we had. The example that we had is the mapping from minus 4 to 4 up to r given by f x equal to x square. This was the function that we had, f x equal to x square, but what is that is lacking in this? If you notice this function f of 2 equal to f of minus 2 equal to 4. In fact, what is that we have? F x equal to f of minus x. That is what we have. So, let us try to look at a function which does not behave in this manner. So, let us begin with a definition. We are looking at a function in such a manner that whenever you find an element in the codomain which is an image of some element in the domain, then what we needed is that the one and only element whose image is that fixed element. So, let us write it. So, let f from x to y, we say that f is 1 1 or injective if f of x 1 equal to f of x 2. Immediately that should imply x 1 equal to x 2. Then we call such a function as 1 1 or injective. Let us do an example. If we look at the previous example, f x equal to x square, then f is not 1 1, that is what we observed. It is not 1 to 1. Now, let us look at one more example. Let us look at a function from r to r given by f x equal to x cube. Now, is this a 1 1 function? Let us now show that f is 1 1. F of x 1 equal to f of x 2. For some x 1 and x 2, then what does that imply? By definition of f, this will imply that x 1 cube equal to x 2 cube. Now, taking cube roots on both sides, we have x 1 cube, the cube root of that is same as the cube root of x 2 cube. Now, x 1 cube, the cube root of that is going to give you x 1, and similarly the other side we have x 2, because the cube root of x 2 cube is x 2. Therefore, f is 1 1. The natural question that one would like to ask here is, in the previous example, why not one take the square root? For example, you have 4, why can't one take the square root of 4 and then say that the function is 1 1? But if you take the square root of 4, then you have two roots, one is plus 2 and the other one is minus 2. So, you have two square roots of 4, and therefore, the function is not 1 1 in that case. Let us have one more example. X equal to 1, 2, 3, 4 and 5, and let us choose y as 3, 4, 5, 6, 7 and 8. Now, define, let us look at this function f from x to y as, define it as f x equal to x plus 1, sorry, x plus 2, right, what we have is x plus 2. Now, let us try to represent this one in a pictorial manner. One, 2, 3, 4 and 5, three, 4, 5, 6, 7 and 8, you have these things. Now, if you notice the function, 1 is mapped to 3, 2 is mapped to 4, 3 is mapped to 5, 4 is mapped to 6 and finally 5 is mapped to 7, right. Here you can notice that each element in the range, that is 3, 4, 5, 6, has got a unique pre-image, right. So, the pre-image of 3 is exactly 1 and there is no other element of x which gives rise to 3 via this f, and similarly for 4, 2 is the only pre-image, and for 5, 3 is the only pre-image, for 6, 4 is the only pre-image, and for 7, 5 is the only pre-image. So, thus f is 1 1 in this case. In the case of, in examples of this kind, where the situation is easy to describe it pictorially, it is always good that you draw a diagram, look at that one, because diagram or this kind of pictorial representation helps us in understanding whether a function is 1 1 or not. Now, let us look at one more concept. A function f from x to y is said to be onto or surjective if codomain of f is equal to the range of f. Whenever codomain of f is equal to the range of f, you say that such a function is onto or surjective. Well, Now, let us look at the same function that we had f from minus 4 to 4 up to r given by f x equal to x square. The question is f an onto function? Now, if you look at this one, the codomain of f in this case is going to be just from 0 to 16. Thus, if I pick an element which is not between 0 to 16, or if I choose any element which is negative, or if I choose any real number which is greater than 16, then there does not exist an x from minus 4 to 4 such that f x is going to give me that real number, right. So, thus if y is less than, let me write it as y less than 0 or y greater than 16, then we observed that there does not exist any x in minus 4 to 4 such that f x equal to y, because our choice of y is such that y is less than 0 or y greater than 16. Therefore, f is not onto. Right. Now, let us do one more example. Let us look at this one, f from the interval 0 1 to r. Let us have it as 0 1 to infinity to 0 comma infinity given by f x equal to 1 by x. Now, is this an onto function? Let y belong to 0 comma infinity. So, this is our codomain. So, let us choose an element y from the codomain. Now, we will have to produce an element x from 0 comma infinity such that f x is y. So, once we have chosen this, our claim is that there exists x in the open 0 open infinity in this infinite interval such that f x equal to y. Now, how to produce this y or how to produce this x? Now, suppose f x equal to y, that is, what does that means? 1 by x is going to be my y, but what we are given is this y. So, that will immediately imply that x equal to 1 by y. So, choose x as 1 by y or choose x equal to 1 by y, choose x as 1 by y, then f x which is 1 by x, but our choice of x is 1 by y. So, this is 1 by y which is going to be, therefore, f is onto. So, thus we have shown that the function f x equal to 1 by x from the open interval 0 comma infinity to the open interval 0 comma infinity is an onto function. Now, let us look at one more important concept of functions of what is known as the composition of functions. Suppose you have two functions f from x to y and a function g from y to z. So, given two functions f from x to y and g from y to z, the composition of f and g denoted g composed with f is defined as follows. So, we will use the standard notation g composed with f. It is the domain of this function is going to be x and its codomain is going to be z, given by g composed with f at x equal to g of f x. Now, let us look at some examples for composition of functions. Let us look at the function f from R to R given by f x equal to x square and the another function g from R to R given by g x equal to x cube. Let us try to compute f composed with g and g composed with x. F composed with g at x, which by definition is f of g x, which is given by f of x cube, which is going to be x cube whole square, which is exactly x power 6. On the other hand, if we look at g composed with f at x, which is g of f x, which is same as g of x square equal to x square whole cube, which is x power 6. You can notice in this case that f composed with g is equal to g composed with f. Now, let us look at one more example. You have f from R to R given by f x equal to sin x and g from R to R given by g x equal to x square. Now, let us try to compute f composed with g and g composed with f. F composed with g at x is going to be f of g of x, which is f of x square, which is going to be sin of x square. On the other hand, let us try to compute g composed with f. Now, g composed with f at x is going to be g of f x, which is same as g of sin x, which is equal to sin square x. So, what we have observed in this case is that g composed with f is not equal to f composed g. So, thus to compute composition, the order in which we compose is very important. So, the composition may not commute, that is what we have observed from this example, that is g composed with f may not be equal to f composed with g. Let us try to look at one more example. Let us look at a simple example, a equal to 1, 2, 3, 4 and 5, B as 0, 1, 4, 9, 10, 16, 20, 25 and 30, and C as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 up to 15. Now, let us look at the function f from a to b given by f of a equal to a square, and g from b to c given by g of b as square root of b if b is a perfect square. Whenever it is a perfect square, define it as root of b, otherwise define it as b by 2 if b is not a perfect square. If it is a perfect square, define it as root b. If it is not a perfect square, define it as b by 2. Now, let us try to look at the composition of these two functions. Let us try to compute g composed with f as a function from a to c. Now, g of, let us write it as g composed with f at a equal to g of f of a, which is given as g of a square, but a square is always a perfect square, and therefore, this is going to give me just square root of a. Well, the choice of square root is only the positive square root, right, and therefore, what you will have is square root of a square, which is going to be just a. Thus, g composed with f at a is exactly a. If you look at the function g, then it looks like a quite complicated function, which is taking one values, that is, which is taking square root of b at some points, and it is also taking b by 2 at some other point, some other set of points. It is quite complicated function, but if you look at the composition, then it is going to be very simple. So, sometimes composition makes things much clearer. Now, let us try to characterize what we wanted. So, we actually started with the following: f of a intersection b is contained in f of a intersection with f of b. That is where we started with. What we saw from those examples is that f is not 1 1. Now, the question is that suppose that f is 1 1, is it true that f of a intersection b is equal to f of a intersection f of b? In fact, the following statements are equivalent. What are our statements? First one is that f of a intersection b is equal to f a intersection f b. Second one, f is 1 1, and third one, for any two disjoint sets A and B, f A and f b are disjoint. The first one is f of A intersection B is equal to f of A intersection with f of B. Second one is f is 1 1. Third one, for any two disjoint sets A and B, f of A and f of B are disjoint. Fine. Now, let us try to prove this statement. Now, let us try to prove this one. 2 implies 1. So, suppose that f is 1 1. So, let us begin with what we know. We know that f of A intersection B, this is contained in f of A intersection with f of B. So, what we will have to prove is the other way inclusion, that is f of A intersection with f of B is contained in f of A intersection B. So, let us proceed this way. Let y belong to f of A intersection with f of B. That immediately implies that y belongs to f of A and y belongs to f of B. Now, y belongs to f of A implies there exists an element A in capital A such that y is of the form f of A. Similarly, y belongs to f of B, that immediately implies there exists B in capital B such that y is of the form f of B. Now, what we have is that we have an element A in A such that y is of the form f of A, and similarly we have an element B in B such that y is of the form f of B. Therefore, what do we have? F A equal to y, which is also same as f B. So, what we have is f of A equal to f of B, since f is 1 1. By definition of 1 1, f A equal to f B implies A equal to B, that is A belongs to A intersection B. This is the one that was lacking in all those examples that we had earlier. For example, f x equal to x square. This is the one that was lacking, the 1 1 was lacking, so that we cannot prove the, we could not prove the reverse inequality. Therefore, y, which is f x, belongs to f of A intersection B. Now, let us look at the next equivalence. 1 implies 3. Suppose that f of A intersection B equal to f of A intersection with f of B. Now, let A and B be disjoint subsets of x. So, what we have is f of A intersection B is equal to f of A intersection f of B. This holds for all subsets A and B. Now, what we are given is that A and B are any two disjoint subsets of x, that is A intersection B is empty. Now, the way we have defined a function it is a function from a non-empty set x to a non-empty set y. So, by convention what we always choose is that the image of an empty set is empty. So, this is by convention, and therefore, f of A intersection B, which is going to be f of empty, is going to be just an empty set, but by our assumption f of A intersection B is going to be f of A intersection with f of B, which is going to be, by our assumption, is f of A intersection B, which is empty. That is, what we have shown is that f A and f B, these two sets are disjoint. Having said these two, now let us prove the third equivalence. 3 implies 2. Suppose that f takes, suppose that f takes disjoint sets, 2 disjoint sets, then what we will have to show is that f is 1 1. So, let x 1 comma x 2 belong to the set X. Suppose that f of x 1 equal to f of x 2. So, in order to show that f is 1 1, what we will have to show is that x 1 equal to x 2. Now, suppose that you have these two, f of x 1 equal to f of x 2. So, let us assume to the contrary that x 1 is not equal to x 2, that is f is not 1 1, right. What we have assumed is that f is not 1 1. Now, we will produce a contradiction. How to produce a contradiction? What we have is that two distinct elements x 1 and x 2, which are x 1 and x 2, but f of x 1 equal to f of x 2. So, x 1 not equal to x 2, that immediately says that the two singleton sets, singleton x 1 and singleton x 2 are disjoint. But then our assumption says that f takes disjoint sets to disjoint sets, that implies that f of singleton x 1 is not equal to f of singleton x 2. That means this set is exactly f of x 1, this is not same as the set f of x 2. What we have shown is that the set containing f of x 1 and the set containing the singleton f of x 2, these two are not one and the same. That immediately implies that f of x 1 is not equal to f of x 2, which is a contradiction. Thus, f is 1 1 or an injective function. Now, finally, let us give a characterization of 1 1 functions in terms of composition and onto function. Let f from A to B, then f is 1 1 if and only if there exists a function g from B to A such that first one g composed with f is going to be just an identity function on A, and second g is onto. You need an onto function g from B to A such that g composed with f should act as an identity function on A. This is what we wanted. Now, let us try to prove this. Let us look at the forward implication. Suppose that f is 1 1, you are given a function that is 1 1. Now, what we will have to produce is a function g from B to A. So, define, well, let us have a diagram at one end. Let us suppose this is x, this is y, you have 1, 2, 3 and 4, and again you have, well, let us call it as 1, 2, 3, 4 and 5. So, what you have is 1 is mapped to 2, 2 is mapped to 1, 3 is mapped to 5 and 4 is mapped to 3. This is the function that we have. Now, define, so let us keep this example as our model and then try to define what this g is going to be. G from B to A as follows: g of B. Now, if you look at this example, natural choice for 1 in y is going to be just 2, and similarly for 2 it is going to be for 1, for 3 it is 4 and for 5 it is 3. So, let us define it as A if B is of the form f of A. So, if you look at the elements 1, 2, 3 and 5 in y in the example that we have, right, all these are going to be, all these are just images of elements of x, and therefore, this makes sense. So, for the only thing that is left out is 4, what we need is an element of x. So, let us fix any element and then any element of x and then let us define it as arbitrarily. So, let us define it as a dash otherwise. Let us fix one element which is not in the range. For that element, let us choose an arbitrarily one element and then map that B to this a dash. So, this a dash is the choice that we make, it depends on one's own choice. So, now we will have to go with proving two things. One is that g is onto, and the other one is that g composed with f is the identity function. Well, let us prove the first one. G composed with f at B at A is by definition g of f of A. If we look at the definition of g, it says the following: whenever my B is of the form f of A, map it to A. Now, I have an element f of A, therefore, this will go to A, which is exactly the identity function on A evaluated at A. This is what I wanted. Second one, ontoness. This G is onto, let A belong to capital A. I will have to produce an element B in capital Y or B in capital B such that G of B is A. But whenever I have an A in A, f of A will be mapped to A by definition of G. So, let me choose B. So, let B choose B as f of A, then G of B is going to be G of f of A, which is exactly A. Thus, f is onto. Now, let us try to prove the reverse part or the converse part. Suppose there exists an onto function G from B to A such that G composed with f is the identity function on A. What I will have to show is that f is 1 1. Let us try to verify the definition. Suppose that f of A1 equal to f of A2. You are given that f of A1 equal to f of A2. What we will have to show is that A1 equal to A2. But once you know that f of A1 equal to f of A2, that will imply that G of f of A1 equal to G of f of A2. This is same as writing the following: G composed with f at A1 equal to G composed with f at A2. That will imply, but what we know is that the composition G composed with f is exactly the identity function that will immediately tell us that A1 equal to A2. Thus, f is 1 1. Now, a similar question that arises is that is there a similar characterization for onto functions? In fact, the answer is yes. So, let f from A to B, then f is onto if and only if there exists a function G from B to A such that first one f composed with G is the identity function on B, and second G is 1 1. So, if you have a 1 1 function, the corresponding function from G is going to be onto, and if you have an onto function f from A to B, then the corresponding function G from B to A is going to be 1 1. Fine. Let us look at the proof of this. Let us again have a similar diagram for the one part. Let me call this as A 1 2 3 4 and 5, and now on the other hand let me have this 1, well let me have a simple set so that things will be clear. 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 1, 4 is mapped to 2, and 5 is also mapped to 2. This is the functions, and what you have is an onto function. So, the forward implication, suppose f is onto, I will have to define a function G from B to A. So, for each, first observe this following: for each B in B, let me define a set A B as all those A in A such that f of A is B. here if you look at the element 1, then this A1 will have 1 and 3 and A2 will have 2, 4 and 5. So, fix a unique A in AB. So, this A depends on the element B. So, let me also write that this is AB. So, that it says that this is from the set AB. So, which means for each B in the codomain I have chosen an element A from the set A. Now, it is clear how to define G from B to A as G of B equal to AB. This choice always exists, such a choice always exists because G is onto. What we will have to do is that we will have to pick one element from each of these sets AB. So, once we have defined this, what we will have to do is that show that first thing F composed with G is the identity on B and the second one is G is 1 1. Well, let us verify one by one. First one, let us look at F composed with G at any B, which is F of G of B, but GB is AB, AB small a b, this comes from the set capital AB. Capital AB consists of all elements of the set capital A which are mapped to the element B, and this small a, the choice is, this is one of the choices, one among the choices, and we have made a unique choice, right, and from that set, and therefore, this is going to give me B, which is exactly the identity on that. The second one, what we wanted is, we will have to verify that G is 1 1. Suppose G of B1 equal to G of B2. Let us apply F on that, F of G of B1 equal to F of G of B2. That will imply F composed with G at B1 equal to F composed with G at B2, but F composed with G is the identity function, therefore, B1 equal to B2, thus G is 1 1. Let us prove the converse part. Suppose there exists a 1 1 function G from B to A such that F composed with G is the identity function. We will have to show that G is onto, let B in B. I will have to produce an element A in A such that F of A is B. So, the best choice is, let me choose A as G of B, then what we have is that I will have to show that F of A is B. So, therefore, F of A, which is going to be F of G of B, which is F composed with G at B, but F composed with G is the identity function, which is exactly B. Thus, F is onto. So, these are the two characterizations that we had. One is the characterization of 1 1 function in terms of an onto function, and the other one is the characterization of an onto function in terms of the 1 1 function. And with this, let me stop. Thank you all.